Hello, everyone. Can you hear me?
Yes.
Good morning, everyone. Thank you for coming to this research seminar. It is for carbon contract 17RD021, and in the title of Utilizing State-of-the-Art FluxSense Mobile Optical Remote Sensing, the ORS technologies for air pollution measurements in California. And the seminar will be presented by Dr. Johan Malmquist from FluxSense. And so I would like first to introduce some housekeeping items. So the meeting will be recorded, so please keep you muted during the presentation. We will be answering questions after the presentation, and please use the question function to type in questions, or you can also email me if you have any questions, or after the seminar, if you have any questions, feel free to contact me, and my email address is here. And also we'll have the slides available after today's meeting. So with this, I will turn to Dr. Johan Malmquist to start the presentation.
Great, thank you.
Johan, could you please share your screen for this?
Yeah, I'll do that. But you need to give me the rights first.
Okay.
Let's see.
I can make you a co-host.
Yeah.
So.
Yeah, that's good. So can you see it? Can you see the presentation?
Yes.
Great. Yeah. Perfect. Okay. So thank you for coming, everybody. My name is Johan Malmquist. I'm CEO for a company called FluxSense that is based in Sweden and in Huntington Beach in San Diego. I'm also a professor at the Chalmers University, also in Sweden. And I would like to acknowledge my co-workers here, Jerker Samuelsson, Brian Offley, and Marianne Eriksson, and also a whole bunch of other people working at FluxSense who has helped out with this measurement project. Okay. So the scope of the presentation, I will go through some of the techniques that we've been using. It's mobile optical remote sensing techniques for the measurements. Talk a little about the principle and how we work. And then I will go through the key findings from a 2-year study that we've done for CARB in several places in California, all the way from Bay Area down to San Diego. Looking at industrial emissions, oil and gas production, CAFOs, emissions from concentration animal feedlots of both methane and ammonia, and then a whole bunch of small sources like landfills and ports and things like this. And we have also done investigation. We've done mapping of air toxic levels in nearby communities to some of these big sources. Methane is one of the key species in this study, and it's an important short-lived climate pollutant and contributes roughly to 9% of California's statewide greenhouse gas emissions. And certain industrial sources are known to co-emit air toxics that have adverse health effects, which, I mean, methane is not having so much adverse effects concerning health. The California Air Resources Board is actually required to use best available techniques, scientific and technical methods to monitor and measure methane hotspots as part of the AB 1383, AB 1496. and the national and statewide emission inventories may be underestimated according to scientific studies. And this is something that we have been trying to look into. And we've been doing real-world emission measurements to try to understand emission behaviors and source level emissions. Okay, so something about our techniques. So our measurement concept, that's a mobile laboratory, which is equipped with several optical techniques, which are fast responding. They're basically within a few seconds. We have like a couple of seconds response time. So the measurements are real time. So you can actually see while you're out driving in the field, what's happening. And again, it's truly mobile. So it's not like we move to a place and stop and then we measure, but we actually measure while we drive. So it's pretty fast of doing mapping and things like this. So what you can actually do with this one, you can actually quantify emissions while you drive. And we have actually two independent methods for that, but I will focus on one of them here. You can do community monitoring, measuring concentrations, and obviously when you do all this stuff, you can also detect hotspots of various species. The mobile optical lab that we are using is illustrated here. It's in a van, and you can see here. Yanju, can you see my mouse? Is my mouse visible?
Yes, I can.
Okay, perfect. Hopefully everybody else then also. Anyway, so our main technique would say is actually that we use the sun as the light source, and we measure the infrared radiation from the sun, and we measure spectra. We have a solar tracker and we have an infrared spectrometer. And we can measure solar spectra. And from the solar spectra, you can actually analyze the column, the amount of the path integrated concentration along the light here, along the line of sight of various species, primarily VOCs, volatile organic compounds, and we'll come back to that. We have a sort of a similar technique, but instead of using the direct sunlight, we actually use the sunlight that has scattered in the blue sky, and we measure, and it's working in the ultra visible and the visible region. And then we analyze that light, and then we can measure some other species, NO2, SO2, and formaldehyde. So basically, we have two column measurement techniques that can measure the path integrated concentration. Then we have also two other techniques, which are basically very similar. It's one, but they measure the concentration at the roof, on the roof, instead of the whole full column through the atmosphere. So basically, we have this multi-reflection cells where light is going back and forth many times, and the light from it's actually a light from a light source. So it's and then it's analyzed with a spectrometer. It's both in the ultraviolet region and the infrared, and so we can actually see what is the gas inside the different cells here. And it's actually the same analysis as done in the column here, infrared and UV. So they are sort of sister or brother techniques. And in the UV area, we actually have two options. We can either do it in a closed optical multipass cell, or we can do it in an open cell. And in this project, we've done it in an open cell that has been placed on the roof. So it's actually, there is no cell, it's actually just measuring the path integrated concentration between the mirrors. An illustration of the problem of our sort of solution here is shown here. Obviously, the oil and gas application. And in this animation, you can see that leakage is actually diffuse emissions, that it's many small leaks. And if it comes to oil and gas, methane is one of the biggest ones, but it can also be other compounds like VOCs. And here you can see how we are doing measurements in this type of plumes. So we are basically integrating across them. We're measuring the column through the cross section, through a cross section of the plume. We are making a sort of, we call it a traverse or a transect across the plume. And in order to identify the sources, we actually do a circle. We measure in a circle around them. Yeah. So in order to, so we basically subtract the upwind. Well, they take the downwind and we subtract with the upwind. Another illustration of the same thing is shown here, where basically we're measuring a column through the plume and we are driving at the same time. And the plume can be pretty high depending what it is. If it's an industry, it races pretty fast. So it can be all the way up from ground up to 100 meters, or the ground up to maybe 600-700 meters or something. And in order to get what the emission rate from the sources, what we do, we measure the gas flux through this cross section here. So the flux is actually measuring across the plume and then multiply with the wind speed. So we need to know the wind speed. And the wind speed you can obtain by wind stations, or you can or GPS zones, or with different optical technique, different electromagnetic techniques. And we are using LiDAR, light detection and ranging, so to measure the wind, as you saw in the previous picture. But again, part of the measurements actually wind measurements, and some of the uncertainties in our measurements usually lies there rather in the column measurement. This is an example of a long-term measurement that we've done in the oil harbor in Sweden, in Gothenburg, where we measured for quite some time, almost 20 years. And you can see how this corresponds to annual emissions and the statistics of the annual emissions. It's the quartiles. And you can see how this is how, in this case, how it's been able to follow, to see that there's a trend actually in the emissions. So that's, and this technique can be used in that you can use it to basically check on sources and to see what is the trend, if it's going in the right direction, or if it's being lower rather than higher, and so on. And if they make improvements, that it actually has some effect. Okay. One of the other techniques that we are using, again, as I said, is a multi-reflection cell, and this is called a mobile extractive FTIR, an infrared measurement, where we have light going in this cell, and we have about 100 meter effective path length there in this 1.3 meters wide cell. So the light is bouncing about 80 times back and forth. Yeah, you can read yourself here some of the more information about the technique. And there's a similar system in the UV. I will not just show that one, but it's so similar. I will come back to what we are measuring in an overlay slide very soon. Anyway, so in order, the techniques are not capable, the solar technique, the soft technique, which you saw before, solar occultation flux method, is actually not capable of measuring all species. So sometimes we have to, and we are doing emission measurements with this solar technique or the SkyDOAS technique. So we are measuring the emission rate by traversing against a plume and measuring the columns. But in order to convert it to other species that we cannot actually measure, then we measure the concentration ratio on the ground instead of the species, the new species we're interested in, against the species that can be measured by the solar technique, the soft technique. So basically, then we can piggyback. We can make a lot of other species that we can measure. So, for instance, when we work, when we measure the data that you will see here that corresponds to methane, then we have not measured methane directly in the solar light because it's not sensitive enough. Instead, we measure the ratio of methane and alkanes downwind on the fence line of sources, and we multiply it with the emissions of alkanes, for instance. So that refers to oil and gas, refineries, and landfills. In the agriculture sector, instead, we are using the ratio of methane and ammonia. And ammonia is something that you can also measure with the soft technique. So this is what we call an indirect emission measurement. Okay, so the techniques that we are using 4 techniques. 2 of them is column measuring. So it's the solar occultation flux method and the SkyDOAS technique, both remote sensing techniques. They measure the vertical column or the path integrated into concentration. And then 2 of the other techniques, they are extractive, and they measure some additional species, and they are used for indirect emission measurements. So for instance, in the UV, we measure the Btex species, we measure the concentration of Btex, while in the infrared, we measure additional concentration of, for instance, methane and a few other species here, as you can read here. And the soft technique, which you could say is our main technique, is focused on measuring alkanes, the C2 to maybe C10. Well, there's no limit really, but it doesn't measure methane really well, and it measures in a way that it measures in the CH stretch region around 3 micrometers, and it's actually difficult to see the individual species. It cannot differentiate between individual species. Instead, it measures it can measure the average carbon number from this. But we've done a lot of tests to show that it's actually you get the mass right by doing it in this way, the total mass, but we cannot speciate too well. Then it can measure a whole bunch of other species, alkenes, and they can actually be speciated because they're measured in a 10 micron region, ammonia, alcohols, aldehydes, and so on. A couple of other species, hydrogen chloride, carbon monoxide. And you can see, and because it's a combination of wind and mass measurement and a column spectroscopic measurement, and the wind is causing most of the uncertainties. The uncertainties are about 20 to 30% on the soft, when we have done a lot of different type of studies. And if you do indirect measurements, they get a little higher because then you combine 2 techniques. Yeah, and with a fast time response of 1 to 5, generally about a couple of seconds with time response. Okay, the techniques are also not capable. The soft technique is not capable of. It needs solar light, and you can see here what kind of condition it needs. So it will not work when it's cloudy, and obviously not in the night. But in these other conditions, it does work. SkyDOAS can actually work in clouds, while the other techniques are working in most cases, except for very heavy rain and snow. Okay, the study that we're going to talk about is that we have been doing is you can see the link here. It's a pretty big report because we've been working on it. We have had multiple campaigns and worked for several years. So everything that I will talk about, you will be able to find in this report. And there's several co-authors that I would like to acknowledge here. Jerker Samuelsson, Brian Offerly, Natalia, Tyggesen Vecchi, and Marianne Eriksson. And again, there's also several more people at FluxSense that has been contributed a lot to this project. So some results from the study. So in October 2018, we did our first campaign, approximately a month, 3 to 4 weeks. And then we focused on looking at the industrial sites in the Bay Area. You can see here that it's the Richmond port area, Richmond refinery area, it's the Rodeo refinery area, Martinez, and yeah, east and west, and Benicia. So what you can see here is actually a solar occultation flux measurement, soft measurement, where the height is correspond to the column or the amount of VOC seen here, and what you see is alkane. So each 10 meter here of alkane, 10 meter here corresponds to 1 milligram per square meter, which is the unit that we're measuring. So this is the Rodeo refinery area. Again, yeah, here. And the wind is blowing from the sea here, so you can clearly see how the measurements, how the refinery plume looks like. And again, we sum up everything under the area here and multiply with the wind speed, and then we get a flux. And if it's just a single source, then we say it's the emission from that single source. But quite often it's a more complicated source, so then we try to divide it potentially into different subsources and several emissions that contributes to this gas flux. Yeah, and again, there's different sources in a refinery. I mean, it can be the storage tank, tank farms, it can be process areas, water treatment, and the process. Yeah, the processes. Yeah. And it's good to get also on-site. In this study, we did not do any on-site measurements, but we have done it in the past, and we are doing it quite a lot on other places. So if you can, then you can actually really identify the sources much better. Now it was the fence line measurements that we did here, and again, we did upwind measurements on this road here. So we did a circle in order to make sure that everything was coming from within here. And you need to do multiple measurements. And we usually say that you need to do 3 to 5 days of measurements. It's a typical what we do if we can, and then at least 4 measurements per day in order to get statistics and to average away some of the wind variability that you otherwise would get, and some of the variability from the site itself, which can be quite high, of course. This is a similar measurement of indirect measurements. And what you see here is a concentration measurement of alkane and methane. The methane is sort of it's actually behind the methane, so it doesn't show up that well, but I guess you can see the blue line. And it correlates quite well with the alkane. So basically, we sum both of them up, and we calculate what's the ratio between these two, and then we multiply with the alkane emission, and then we can also say something about the methane emission. Of course, this assumes that it's a well-mixed plume and some other stuff. So you need to do a lot of statistics in a similar way as the soft. So again, all the methods that we talk about now are based on a lot of statistics, which is very important in order to take away the atmospheric variability, which can be quite high. Okay, so these are the 4 refineries. These are some of the refineries. These are some of the results. So we did about 3 to 5 measurement days per site, and for each site corresponds to about 18 to 20 individual measurement transects or traverses across the plume, and it includes upwind measurements and downwind measurements. And what you can see here is the alkanes, and you can see SO2, and you can see NO2. I should point out that SO2 and NO2 are measured by the UV, the sky DOAS measurement. And that technique, it can only measure NO2, and the NOx that comes from a source is usually NO in a stack, and then it's converted quickly by titration to NO2. So we are sort of missing one. We are missing one part here of the NOx. If you're enough far away, then usually it's the NO2 corresponds to about 80% when it's steady state of the total NOx. So that means that we will underestimate the NOx by about 20%. But if you're very close, then you can run into trouble. Then it's very easy to underestimate the NOx actually, because then you are missing a much bigger proportion of the NOx. And here are the corresponding methane emissions from these three different sites. Again, they are derived by indirect measurements by, as I said before, by taking the ratio of two species of the alkane and methane. And for some of these, sometimes it's when it comes to the methane, it can actually be difficult sometimes because there can be interfering sources. So, for instance, in the Richmond refinery, there was a landfill just side by side, which was actually a very big source of methane, and it blew in, and there was a wetland, and it blew in, and you need to be able to see the difference between what is interpret what is the refinery and what is the landfill and so on. Here's also indirect measurements of the Btex, where we have taken out also in particular the benzene, that part of that Btex. So the benzene is actually part of the Btex here. So yeah. So for instance, for the we can look, if we look at the Richmond refinery here, we can see we have 39 kilos per hour in total of that one, and then we can compare that to about 300 kilos per hour of the alkanes, and typically the Btex is around 10% of the alkanes. It's usually an order of magnitude smaller, and benzene is basically 2 orders of magnitude smaller than the alkanes, because it's a small part of the Btex. Mostly it's toluene and other things. Okay, it's now we have in this study we have compared the data, our measurements to inventories, to the carb emission inventory data for 2018. So you can see here in blue and yellow, and in blue is you can see the alkane measurements done by FluxSense in blue, and in yellow you can see the carb VOC inventory. So you can see that for the different refineries here. If you add them all together, there's actually a factor approximately 2.5 or something between what is in inventory and what is actually measured. And you can do the same thing for the indirect measurement of the methane that we have been doing. So then you can look at the inventory in black, and then in green you have the measurements. And then you can compare the green and the black color here. Again, that's also a discrepancy, approximately same size, I would say. There is, of course, there's one systematic thing with the soft method, because it can only measure in the daylight, and it's in the solar conditions. So in such conditions, the emissions of the tank emissions, they will be higher than they would be in the night in the same conditions, because the solar light is driving some of the emissions, and also sometimes the ambient temperature, but most of the time so the solar light has an importance. And we have done in the past, we've done quite a lot of sensitivity studies looking at what you would call the API, the model that the refineries are using themselves to calculate their emissions. And there are diurnal variations in them, which are typically like something like 30% or so. So it could be likely that we are sort of underestimating the annual emissions by maybe 30%. So our data, if we would make them analyze them, that would be 30% higher. But still, there's sort of a gap between the measurement and the inventory. Yeah. And what you can do, you can compare, you can calculate discrepancy factors so measured against inventory. And if it's 1, then it's pretty okay. And if it's higher, then there's a discrepancy. And I already spoke about the VOC discrepancy, which is varies between 6 to about 1.36 to 6 here for different refineries. But if you look at the NOx and SOx SO2, they are actually closer, much closer, which you would expect because they are coming from chimneys or from stacks, which are usually monitored in a better way. At least the NOx is monitored. Sulfur is usually calculated sometimes with amount of sulfur in the fuel and so on. Yeah. We can compare these refineries to other measurements that we have been doing worldwide. Actually, this corresponds mostly to Europe, but and other parts of the United States like Texas, and also it also includes China. And Middle East and Korea. And this is individual refineries. So you can see the yellow parts here. It shows the emission factor, kilo emission per capacity of that refinery. So it's like an emission factor. And as a function of the measured emission that we have been doing here. So you can see that the yellow refineries, which is the Bay Area refineries, they are in the lower quartile or even better compared to many of the others. So that's sort of a general remark that I mean they are in pretty good shape, these refineries, compared to other refineries in the world. So yeah, so this is basically conclusion from the study is that the Bay Area refineries were low on a global and European context on the lower range. However, there are still discrepancies, and discrepancies were 2.5, and this discrepancy on average, and only a smaller part of this is actually in our what we think in our experience is actually caused by this diurnal variation that you have due to the solar light and to some of the other wind and meteorology. Okay, I'm now switching gear to the second campaign that we did in the project. And now we were focused on oil and gas production. And this is in the Central Valley, San Joaquin Valley. And it's in the Bakersfield field, near Bakersfield, north of Bakersfield. You can see here some, well, the yellow shows where there are sort of different source areas. And well, there's some triangles showing where we actually did measurements with some of our wind measurements and so on. And we did these measurements in October 2019 and in May 2019. What you see here is some of the production rates from 2018 from the Kern County fields, oil fields, and they are which are sort of in this study area. So this is what we were studying. And actually, this corresponds to more than half of the California oil production, and 3% of the U.S. one. So it's well, actually, yeah. So that's the fields that we measured. So we've been able to have a look at more than half of the California oil production in basically one project. So you can see here that there are some that and it's differentiated in pure gas production. Methane gas and oil and condensate, where there is other VOCs like, and one of the ones that we have been looking at quite a lot is for instance alkyls here. So this shows a measurement transect, a measurement upwind and downwind, making a circle around the alkyls oil field area. It's actually it's difficult because we have to measure on the roads, and it's actually it's not a pure alkyl because some of the other oil areas, oil fields, they actually are also within this measurement circle. So we measured, and you see the wind direction here. So some of the Midway Sunset actually were in our measurements area, and also Buena Vista here. But but we covered the whole Elk Hills as well. But we have some of the, when we claim that it's an Elk Hills, it's not always a pure Elk Hills. But on the other hand, we have also been doing the measurements in some other wind directions where some of these other sources may contribute less also. It's quite a long measurement. It's actually about almost 100 kilometers. So it takes quite some time. Also, it takes almost an hour to go around here, even though the roads are quite isolated and not too many cars. So, and that should be compared to, so this is a much larger areas, and that puts a lot of strain on keeping the instruments in good shape and not having drift in baselines and so on, because a lot of the emissions can be in the baseline. And it's very important to repeat this multiple times, many times. Here is the same type of measurement, but measuring, this shows the concentration. I guess it may be, I don't know, I don't know how easy it is for you to see, but the color scale here corresponds to the concentration, and the concentration is in milligram, not in micrograms. You have to multiply by 1,000 to get microgram, or something that is close to ppb. So this is sort of ppm levels, you could say, when it's one. And you can see that this both, you can see distinct alkanes and you can see distinct methane. And we did again the ratio on the ground of these two species, and from that, this is how we have obtained the methane emission. So basically each field we have been between 2 and 8 days at. So some of them we've done more measurements at Elk Hills. We did a lot of measurements on that one. And some of them we have done less, and it corresponds to 4 to 13 measurement transects. You can see the alkane emission, and you can see the methane one for some of the main oil fields that were main studied areas that are, and which are very important, which are big sources, big oil producers in this area. And at the same time, there were actually on single days, we had as part of the project, CARB, they contracted Scientific Aviation to make airborne measurements. So they were flying with a methane laser sensor, a Picaro, in an aircraft, and making circles around the different oil fields, around some of them, around 2 of them actually. And we measured at the same time. So it's sort of simultaneous measurements. And you can see the alkyl measurement here, where you should compare our in green methane measurement with the Scientific Aviation in yellow. And you can also do that for the Simric-McKittrick area here instead. Here's there's a factor of 2, and here's that about 20%, 30% difference. At the same time, you should remember that we claim that for the soft measurements has about 20 to 30% uncertainty, while the indirect measurements have 30 to 40%. So that would sort of be within that uncertainty range. And of course, an airborne measurement is sort of a snapshot very much, that it goes up and then it goes down again. It cannot do so many, it cannot cover the whole column in once. So it has to do that sequentially. And so there are like uncertainties, obviously, also in the airborne measurement that you should consider. Yeah. So the oil fields here, they are not, so we have calculated the NMVOC and methane emissions based on basically production rates that are published from each well, from the 2018 18 production figures at field level. And then we have applied emission factors by several entities, the EMF, EEA, and IPCC. So sort of overall standard emission factors to get the emission rate here. There are some uncertainties here, and there's not so much. There's still a lot of work that needs to be done here, obviously, because you cannot really get a good emission inventory for these sources in the way that the refineries have been understood. So, for instance, here the alkyls here in total here this alkyls according to these calculations, emission factors plus production rates, we get that it should be about 56 kilos per hour of NMVOC coming out, non-methane volatile organic carbons, while about 1 ton of methane. When we compared it to our measurements that I go back here. So if you look at alkyls again, we had about 1 ton alkyl, yeah. It's about 1,000 kilos per hour of methane, while both our measurement and the scientification measures considerably higher for the methane. And for the alkanes, it was only 56 kilos, and here we measure 3,300 kilos. And this is where we see a much bigger discrepancy, the biggest discrepancy we see here. And overall, if we look at all measurements that we did, we can see that the methane emissions were 2 times higher than the production-based emission factors, while the non-methane volatile organic carbons were actually 10 times higher. So there's a big discrepancy here that needs to be further understood, I think. Okay. So now I go to the third campaign, which is where we again shift gear, and now we talk about dairy farms or concentrated animal feedlot operation, CAFOs, and at the same time, and it's also in the same area as where we had the oil fields, so it's near Bakersfield area, up to, and also to Lara and Merced. So we were in some different places here, which were picked out by CARB as interesting CAFOs to study. Some of these had digesters taking care of the animal waste, while I guess 1/3 or something had it, and the other ones did not. And it was interesting to study that. And we measured in both October 2018 and in May 2019. Here is an example of a CAFO, and in a CAFO there's about, it varied a little, but between maybe 3 to 8,000 animals. And we got the animal statistics from, well, we got them, but there are some uncertainties in the statistics because they are yearly, and you don't know if there's been some animals that have been sold or slaughtered and so on, and how many came back and so on. But part of the numbers that we do is that we do it per animal head, the emissions in the end. So you can keep that in mind. So what you see here on the left side is actually a color-coded soft measurement of ammonia. You can also see the same measurement as the blue line here. So this is a very distinct ammonia plume from this CAFO here. At the same time, from the same CAFO, we measured the ratio of methane and ammonia here. So, and it's also NO2 shown here, but if we focus, and so the blue here is the methane coming from the same CAFO, while in red is the ammonia. You can see that this ammonia that we have, it looks sort of similar to the one that's measured by SOF, but again, this is on the ground concentration, while the other one is the column, is the path integrated concentration. And then we take the area of the ammonia and we divide by the area of methane. Well, actually vice versa. and then we multiply with this emission rate, and then we get also the ammonia emission. So if we do a lot of averaging on these ones, we studied I don't know how many, 1, 2, 3, 12 or something different CAFOs over, and we measured some of them we measured 3 days, 3 independent days, and some of them we had only time to measure 1 day. So 1 day measurement, and for each of them we had 7 to 14 measurement transits. And you can see, so each of them shows here the gram ammonia per head and hour coming out from this. And what you see here is different farms: West Tulare and South Bakersfield and North Bakersfield, and and you can see statistics here. You see the median value and quartiles and things like this in this graph here. Same thing for methane. It looks like this for the same refinery. So you can see on overall we had about 15 grams per head an hour from the ammonia, and about 40 for the methane for the same CAFOs. We did compare these to the California greenhouse inventory. And if we do that for these emissions for the different farms here, now it's not per head, but it's then it's the absolute emissions of ammonia here, of methane, sorry. So then you can see that it's for many of them it's not too dissimilar. There are some discrepancies, some big differences in some of them, and again, blue is measured and the red one is inventory data. So you can actually see that the measurements are somewhat higher, but not like an order of magnitude or anything. It's actually 50% higher than the emission factor models. Doing the same for ammonia, then we used older emission factors from the EPA 2004, which was basically and if we did that, then we actually got 100% difference between our measurements and what was in these models. However, the ammonia is known to have a diurnal variation because of the sun driving some of the emissions. So we know that part of this discrepancy is actually caused by that. So that needs some further investigation. Okay, I'm switching gear again. So basically we did this industrial emissions. We have done oil and gas, and we did the dairy farms, CAFOs. And then we also did a last study down in the South Coast Air Basin, going from North LA down all the way to San Diego. And then we focused on some of the some different type of sources. This is in North LA. This is the Sunshine Canyon landfill and the Placenta oil field north, for instance. Also in the north, we looked at some breweries and also some landfills and smaller oil fields. And in overall, I mean the breweries, we saw emissions from all of these, and we could not. Yeah, but we could not see from the landfills, and we only saw emission. We saw distinct emission from the ones that were in operation. So the older landfills, we were not able to see much emissions. Yeah, we don't have so much statistics in this study. We were doing more snapshots because it was sort of a follow up some different leads as in the fourth campaign, which was also a much smaller one. It was a 2-week study instead of a 1-month study. we went down to south coast to Huntington Beach area, where we did different landfills, Coyote Canyon landfill and the Frank Borman landfill. And then we were down in Huntington Beach area where there's some oil fields here we were studying. And for instance, this is the Huntington Beach oil field area, and you can see here in this Google Earth plot the columns from different sources. So there are quite some distinct sources in this area, but I mean they are not super large. If you add them together, it will not be. It will still be like 10 to 20 to 30 kilos per hour coming out from different places, but very distinct. You can see here drive on the shore here going from south to north, and the wind was actually blowing out. It was from the east blowing out to the sea, so we had a very distinct peaks, and we could actually find different sources here quite easily while doing this. We also went down to San Diego and did measurements, and then basically this shows, and we saw mostly NOx and SOx that we could attribute to all the ship traffic that there is there, heavy type of ship traffic. So quite distinct sulfur emissions and obviously NOx. To the left here, there's the airport, but all these other parts is the harbor. This is sort of a summary slide. I know it's very busy, but it's the report is public, so you can, if you're interested, you can just go and get more details in the report. But basically, this slide is actually 3 parts. So the left slide is the San Diego area, it's the San Diego Air Basin. So it's different, and then we have the middle part, which is the south part of the South Coast Air Basin, and then the right one is the north part of the South Coast Air Basin, and it's divided into alkanes and methane. And you can see that the methane here is dominated by the landfills from where we had measured quite a lot of emissions. Okay, switching now gear to community measurements. So basically, the emission rates are of course very important to understand. Well, if you have emission rates, then you can actually model what's the impact on people living close and living in the region. And some of the emissions of this type of diffuse emissions, like from the oil fields, will have a regional impact quite a lot, but they may not be. So they will rise very quickly and so on. So how much they affect on the air quality side, that's another question. Anyway, so we did concentration mapping, primarily with the mobile extractor FTIR and the DOAS instrument and the UV visible one, and both measuring the concentration at roof level. So we were in the Bay Area. We were in the Richmond AB 617 area, Port of Richmond, Iron Triangle, Central Richmond, North Richmond, and Marina Bay. We were also in Bakersfield at some different Meadowview, Highland Knolls, and near Avon. And in the San Joaquin Valley oil fields, Lost Hills, Derby Acres, and McKittrick, and then we were in Port of Stockton. This shows measurements, and several of these measurements we actually did in the evening or night, because in the day the concentrations are they lift quite fast, the gases, and so there's a dilution in height in the day driven by the sun. So it's much sort of easier to do this measurement in the night. It's more distinct. And what you can see here, and in the what you see here is actually the Richmond area, and you can see here how you can actually map things here. And it's possible to follow a plume downwind or upwind to find the source. If you find something, you can go upwind and find the source. this is an alkane drive in the Richmond area, for instance, where we saw a lot of impact from the port here because of primarily southerly wind. Here is the Btex concentration mapping. This is in Bakersfield area, Bakersfield, inside Bakersfield, and you can see here hotspots of Btex. The unit is in milligram per cubic meter, so multiply by 1,000 and you will get it to ppb or microgram or to microgram. And in general, when we have been doing this measurement for Btex, we see that it's kind of we do get plumes every here and there, but we don't really have repeatable plumes so much. So it's a lot of things coming from mobile sources and things like this, and we have not been able to see so much from the stationary sources, such as the oil fields. So that's sort of a general conclusion that we haven't been able to really see too many hotspots from the oil field sector. This is a similar measurement in Lost Hills, driving around, where we've been able to again find different hotspots, but they have been, as you can even see here, left to right here. This is the same day, 2nd of May 2019, in the evening, and just 1 hour between. If there was, and you would assume that you have the same type of pattern here. In some places we have not been driving exactly in the same places, but in general we have not been able to see, we have not been able to see so many consistent patterns with the Btex, even though we have very distinct plumes every now and then, and the response of the sensor has been good. This is the Btex doing an average of all the campaign measurements in the Richmond area. I showed before the Alkane measurement in Richmond, up in Bay Area. Now instead, what you see here is an average for the whole campaign and for several days, and it's predominantly in southerly winds, south winds, and the symbols here, they correspond to the number of measurements. So you can see here the circles with the bigger they get, the more measurements we have. And you can see that there are like hot spots and things like this, and it's very much close to the harbor where we had it, and it was again southerly winds most of the time. And in general, when we did this measurement, but basically because we most of the time had southerly winds, we did not see the impact of the refinery, which was up here to the left, which was up in the northwest. So we saw mostly the impact from the port, that the Richmond area here was impacted quite a lot by the port. And this is a bigger, the same thing, but for alkanes, and it's mapping a larger area here. So, and while doing this type of mapping, we find, for instance, the pipeline that was leaking up here and things like this. And you can also see you can also see the plume that is moving from south to the north. As just a side remark here, while doing some of the Bay Area measurements, but also in the South Coast measurement, I mean, it's been it's been a lot of fires in between 18 and 19, as you know. So that has well, it gave us actually some possibilities to do a good fire measurement here when there was a big fire here at the Traverse Air Force Base. So you can see a soft measurement here with a lot of different stuff where we could see very clearly in the columns. Not so much on the ground though, because it races quite quickly, but very, very good measurements in the column here. But this also had some sort of impact on us that we were disturbed by quite a lot of fires, and and we had to deduct some of the things that we got in our spectra, and it gave us sort of high backgrounds of different things. Okay, so I'm now up to the conclusions. So we've done quite a big we have a big coverage in this study, geographic coverage, and also several sectors and source sizes. For campaigns, we've gone from Bay Area to San Diego. We looked at the major refineries in Bay Area. We have looked at several landfills in the region. We have been able to measure more than half of the statewide production capacity of oil and gas. And the measurements range from single well to entire oil field emissions. We have studied 20 dairies. And some of the conclusions that you already heard is that the Bay Area emissions of the alkanes or NMVOCs were about 2.5 times higher than the inventory emissions. And while the methane emission was 3 times higher. But overall emissions were low in a global context in an absolute. In the South Joachim Valley, the oil and gas emissions, they totaled about 7 tons per hour of methane and 10 tons per hour of NMVOC that we identified. And these numbers are considerably higher, especially with the NMVOCs, than you get with the emission inventories. Sorry, I made a mistake here. There's a typo here. And we looked at roughly 20 dairy farms. And for the methane and ammonia, we saw that there were discrepancy of about 50 to 100% comparing to the annual emission inventories. But some of the discrepancy can have some explanation due to compilation of inventory data and the survey diurnal or seasonal biases and number of animals. We have seen relatively fewer occurrences of high ground level aromatic concentrations during the service. And that concludes what I wanted to say. And please have you will have the report and of course this talk and this presentation. But there's a lot of more information in the report than I was able to give during this short hour. Thank you.
Thank you, Johan, for the great presentation. So now we have time for questions. If you do have any questions, please type in the chat and I will read out to the PIs so they can have answers for your questions. And again, the slides will be available after the seminar and we'll share the link to everyone. And also we have the report for this project already available on CARP's webpage. So feel free to check that out if you need further more details. I'm not seeing any questions in the chat yet, or I guess maybe you can also raise your hand. I will check from the screen. Okay, there's one question. So there's a question asked, how long does each measurement take?
Could you, I mean, because I spoke about a lot of stuff here. So in which do you have a specific application in mind that I was talking about, or in general?
Rosa, could you please unmute yourself so you can just ask the question if you don't mind? In general.
Okay. I mean, of course, it's the thing is that we have there's sort of a standard on how to do this, the soft measurements, and that standard says that you need to average away a lot of the variability of the metrology, because that creates, so if you just do a one snapshot measurement, just one transect, then you will have variability, and your uncertainties will go up. So the measurements, if you do a refinery, if you want to just have one snapshot on a refinery, that's one transect, it takes only 5 minutes, 10 minutes around that, or 15 minutes around, 20 minutes around that refinery. If you want to go around the Elk Hills oil well sites, it takes an hour because it's 100 kilometers to drive. So it depends on the size, obviously. And you need to repeat this several times in order to average away the variability. And this is why I was saying that it depends on the application.
So Cynthia, could you please unmute yourself?
Sure. Hi, this is Cynthia Garcia from the Research Division. I have a couple questions. I think her question may have been similar to mine. I was wondering how long you stayed at a different area when you were doing your drive-bys. And then the other question I had was, you mentioned that you're not measuring at nighttime. Is there any pollutants you think would maybe be greater because of the inversion that is in nighttime at the community? And were you able to, I assume you weren't able to measure at the community during nighttime either. And then the third one, you mentioned that in the South Coast, you weren't able to see as high alkane and NOx and Btex as compared to in the Bay Area refinery and the oil field. Is that correct? Thanks.
Okay, now my brain, no, there was 3 questions in one. Let's see now what you said.
Okay.
You ended up, you talked about the SOx and NOx, that there was a difference in that. I don't think, I mean, we did not do the same. I mean, in the San Diego and so on, we were looking at it was the port emissions basically that we saw, and airfield emissions of SOx and NOx, and there's not any big industry, there's not like refineries and things like this. So we measure SOx and NOx from what I would say is shipping basically, and airport. And while up in the Bay Area, it was the refineries basically.
So you didn't measure anything that is oil or gas or refinery in the South Coast? Or dairies? Obviously there's no dairies there.
In the South Coast, we measured oil and gas wells, oil and gas production. That's what we measured. But I mean, and then it was not so much SOx and NOx from that, obviously. So,
right. So I think
no,
that's what I was
we did not measure the refineries in the South Coast because we're actually doing that for the AQMD, to be honest. So we are not allowed to do that. So I mean, there was no reason to do it because.
Understood, but the oil measurements from the oil fields was less than what you observed in the San Joaquin, right?
Aha, you mean in terms of it was I mean in the San Joaquin it's like a big oil field and it's like a big production. It's like we can look at aggregated averages of things like this, but when it comes to a specific oil source, I mean it was more individual oil wells down, or a couple of oil wells down in the South Coast, like in Huntington Beach. So it's not so we were not able we need to do some more studies then to make any, I mean, generic, we can see that we can see the emissions, and we could of course multiply it by how many wells there are and so on, but there's quite a lot of variability in the wells. So I think that, and yeah, so, and there are, yeah, so you would need a little more statistics in the South Coast to actually, to say something of, generic value of something, to say something about what's the annual emission or what is like, or extrapolate it to something else. Because now we measured what we did, but it was not, it was like, and it was many important sources, but we have not been able to package that into something that I would say it needs further studies if you want to do something there.
So the wells, how many wells are there in Huntington part where you drove around?
I mean, the thing is that field is it's more open wells up in the San Joaquin Valley. It's while it's more closed down in the Huntington Beach. So there's like so they're not all active. That's the thing.
Okay.
And I cannot say. Then I would like to get help from my colleague Oaf.
I'm just trying to understand, because we had a study of health and we did see a lot more effects on the San Joaquin oil fields, and we didn't see so much in the South Coast. So I was wondering if you also observed that you didn't have as much concentrations there.
Yeah, but are you talking about SOx, about sulfur, about NOx, I think, or are you talking about the VOCs now?
No, whatever you would measure around an oil field, combined.
Yeah.
Everything.
Okay. Yeah. because I mean, our main thing around the oil fields has been to look at the VOCs coming out and in terms of in speciated in different ways, and to measure the concentration of them and basically trying to follow them. And it was very clear up in Richmond area and so on. And it has been it's been more difficult to follow them in the San Joaquin Valley. And also, but we didn't measure in the night. I mean, we measured in the night and evening. This is when we did the concentration, the community monitoring we did and because this is where you get the high concentrations, and it's also easier to do the measurements and so on. So we were focused on the late measurements for the concentration mapping. Because you were asking if there's some other speed, if there's something we are missing, if there's a daytime, if there's a diurnal variation in some of the species, so that they could be higher in the nighttime. And obviously things are higher in nighttime because there's inversion. I mean, there's not so much movement in the air. So that's for sure. But I'm not sure if there's and of course there will be less chemistry in the night, so there will be some things will not degrade as fast. Something will stay, of course. Some species that could react in the day.
But you did measure in the nighttime then?
Yes, we did.
Okay. Thank you.
So thank you, Cynthia, for your question. So we'll get some questions from the chat. There was one question regarding in one slide, you list NO2 and N2O or NO2 emission from animals. I guess they mean like dairies. I think you had one slide talking about emissions from the dairy farm, and you have a couple of pollutants. I think this question was asking whether you have listed NO2 concentration from these animals. And if you have any follow-up questions regarding your question, please feel free to unmute yourself and what kind of details you would like to get from this part.
I see there's a discussion in the chat already about, and it was actually my colleague Oaf who did that plot. So now I'm a little uncertain. I saw it was NO2. He claims it's the type.
Okay.
The image laden with N2O should be correct, but I think that
N2O would make more sense.
Yeah, but we did measure NO2. We saw NO2 also, but I mean it was from some type of combustion source or something in some places. So, but it was not our measurements. I would say that our measurements of the nitrogen species are more uncertain when it comes to the CAFOs. I wouldn't. We have not pushed them very hard in the report.
Okay. All right. Sorry. Let me go through the questions from the top. So another one would be: do you see differences in methane emission from dairy operations with and without methane digester and collection systems?
Yeah, a good question. And no, not too much actually. We were really wanted to see it. We were differentiating between them and so on, but it's not within the, I guess within the variabilities and so on. It was not it was not a significant difference enough for us to claim that there was that they were so, because I mean they should be. So that's something that we were not able to see.
Okay. So what are the implications of this data for California's greenhouse gas emission control strategy?
Yeah, I mean I guess I mean, we have measured a lot of emission, obviously, from the oil and gas production, and the inventories that we did, we basically combined emission factors with the production rates. And obviously, when it comes to the non-methane species, there's a big discrepancy. Of course, they are not so much greenhouse gas driving. I mean, but some of them can actually produce ozone, which would then be greenhouse. So I think that that's something, an order of magnitude difference is something that is like, is important. When it comes to the methane, I mean, we had a factor 2, but we also had in some places much bigger differences. So I don't know what is the, I mean, I'm not probably the right person to tell you what is the control, what is the implication. I mean, this is probably you who should tell, you know, take our data and say that this is how it can be used, and whether you need some more studies and things like this.
Right, Johan, this is Abhilash. I'll chime in to add to what you're saying. Abhilash Rajan from ARB. This is an important research. I think, as Johan mentioned during the presentation, these real world measurements are really critical, right? Because, you know, it gives us a way to really, you know, see what is happening in the real world. It gives you an opportunity to do real world checks. At the same time, these are snapshots, right? It is an hour during the day. It doesn't tell you what happens throughout the day when activity changes, you know, at these facilities, you know, what the feeding time might be in the dairies, and, you know, there are a lot of differences in operations that change emissions. But you have to take these snapshots, you have to take this information in a kind of a portfolio approach. What Johan's work, what FluxSense allows you to do is look at the entire facility emissions. And we also have other kind of work going on, which allows us to see, you know, large point leaks, or, you know, emissions from scientific aviation. That's also a snapshot. You have to take all this information, use it in a complementary manner to evaluate, you know, the entire portfolio approach, really, right? To look at the entire emissions. This has happened. This kind of work has happened in the mobile source sector. You take real world emissions data, real world data, to inform, you know, inform our source understanding. And so it's important to look at it, you know, comprehensively. I think Johan mentioned, you know, a lot of work still needs to be done. This is kind of the first step, and we're taking the information, using that to understand the source behavior. Also important to recognize that this will be kind of complementary to kind of the kind of work South Coast has already funded. FluxSense has done a lot of work with South Coast AQMD, you know, building systems for them, and they have collected data from their refineries, their sources, and this project allows us to look at the rest of the state and use all this information comprehensively, and also build capacity, right? Know what kind of state-of-the-art systems are out there. How do you use them to understand source behavior, as well as, you know, air pollution in communities? So it's part of the bigger picture, but as Johan rightly mentioned, a lot of work still needs to be done.
Well, thank you, Abhilash. So let's get to the next question. Could you discuss the opportunity of using these techniques for measuring mobile source emissions, like emission from vehicles? Have you done any work related to measuring?
We are doing, yeah, not. I mean, mobile shipping and things like this, bigger stuff. And I guess we could work with, you know, working equipment and working machines and things like this. When it comes to measuring, well, actually, to be honest, we did see leakage of the LNG buses that you had in LA during the project. There was quite some leaks we detected, but we were not making. From this LNG buses, they were basically definitely leaking methane. So I mean, we have our capabilities because we are mobile. We can stand still, or we can move, and we can scan. So I guess it depends on what is the question you want to ask with the mobile source emissions. We haven't done too much on like, I mean, cars and trucks and things like this, but it wouldn't be. I mean, we could do it because we have a broadband technique both that can measure many species, and we do measure the CO2 and carbon monoxide. So we have the combustion species, so we can measure emission factors and we can do things like this. We have done it in the past in like in Mexico City in some research projects, doing this, looking only at the mobile emission at mobile sources to understand what's the aggregate, what's the average, emission factors on different species, formaldehyde against carbon dioxide and so on. So again, it depends a little what is the question, but I mean, I cannot really say that, that we've done a lot so far, but I mean, we would be happy to do it.
Well, I guess my question was that, I mean, CARB already has roadside monitoring that's going on. I work with the PEAKS group in mobile source emissions. And, we're always looking for additional measurements that can complement what we're already quantifying from emission factor standpoint. So, I'm interested in the idea that we could also get VOCs. And I guess one of the questions about applicability is, are we going to meet detection limits? Are we just putting out a piece of instrument? The other thing is, we actually do this where we're watching the plume of a vehicle go by. So the data collection rate or how fast, we see a plume for a couple seconds and then it moves on. And so the question then is, are these instrumentation and these techniques able to fit within those timeframes? And since I guess since I'm asking questions, the other one is, how do you deal with mobile interferences as you apply your techniques to understanding and estimating sources? Because mobile sources are going to be ubiquitous. So I guess I've now got two questions for you.
Yeah, I mean, it's a good question. I mean, when it comes to dealing with the interferences and so on, the column measurements are actually pretty insensitive to the ground concentration because it's a big column. So we measure something. So it's both, and usually in the baseline. I mean, we have a baseline and then we get into plume and out, and so the variability in the baseline will tell us if there's some effect. But for instance, for the alkane measurements or something like this with a soft, it's not so sensitive. Of course, the concentration measurements can be sensitive, especially the aromatic, the Btex measurements. We have some occasionally problems when we are passing a gas filling station, or sometimes standing in a corner and so on. So, but I mean, most of the time we are not in a plume. So we are looking at the baseline if there's some problems like this, and we have also been focusing on doing some of these measurements in the night or late when there's much less traffic. So it's more that the car is passing by and we get a peak, rather than we are more concerned if there's something in the baseline, because we are sort of working with baselines. I mean, slow and things like a little slower things than in just 1 second or two spec. Then maybe we interpret it. So it's a good question, and it's something you need to be awake. And of course, we have carbon monoxide and CO2 as our species. So we can, if we are really want to look at it, then we can go back and have a look if that it was correlated with some of these species, for sure.
Johan, if I can add to answer to Michael's question. Michael, Johan definitely talked about the technical capacity, right? What the system can do and at what level it works. I think one way to think about is this kind of system is so unique. The capacity may be much more realized if you study big sources like facilities, right? Ports and data that Johan presented. So if you wanted to study mobile sources, like mobile source facilities, like a large freeway, I-710 freeway, right? And you do that kind of a measurement downwind of it multiple times, you can get the total facility-wide emissions over a longer time, and then correlate that with the activity. So how much vehicle movement you have. That kind of a application might be better for the system, because then the enhancements are significant. You have a lot of vehicles active, vehicle activity, emissions are high, you can estimate that. If you wanted to look at individual sources, I think there may be other techniques, other systems which have better resolution, better fast response, and they can also measure concentrations low enough that you can correlate with individual vehicle. I think the best application, as Johan really very well showed here, is the facility level. So that may be a better application to think.
And
I mean, if I just add, I mean, it's the techniques are fast, and we have about the ppb detection limit. But of course, there's all these other more fancy state-of-the-art instruments like PTRMS and things like this that have a better detection limit and can be so on. So it all depends on what you're after. But again, since we can measure some of the other the CO2 and CO at the same time and N2O and things like this, you can do work where it complements some of the other instruments, because it's kind of a unique range of species you can measure in the infrared. It's a broadband thing. So, but it's again up to what you're interested in, So it's yeah.
Yeah, Michael, and I also want to add that, so this is, our project is based on the system they built as a mobile van to really measure facility level emissions. But Johan, if you correct me if I'm wrong, but they do also provide like individual instruments, which could be used for stationary monitoring. Potentially can be integrated in for a system like Btex to really understand the concentration at a certain locations when you try to detect plumes. And there are some specifications mentioned in the presentation as well as in the report, talking about the detection limit of these instruments and also time resolution of these instruments. So if you're interested in that part, feel free to take a look at the report if you have any more questions, and we can reconnect you with Johan to get answers from him. And also, I think there's Peter also mentioning in the chat and echo Johan's point, PTRMS actually have the sensitivity and the temporal resolution for, really measure concentration, VOC concentration from vehicle emissions, if you're interested in that as well.
Yeah, that's great. I mean, yeah, so I'm familiar with these other, techniques. I guess, the key is I want to get really, really good data for really, really cheap. And, I think, which is what we all want, right? And so, and that's kind of my, one of the other assessments of this is, if this technique may not have the lowest detection limit or even the fastest data collection rate, but if it's significantly lower cost to operate or capital purchases, that's another thing that I think is valuable. So yeah, I'll look at the report and certainly, and I think I'll follow up with Peter about the time of flight stuff.
Yeah, and also feel free to let me know if you need more information regarding the cost or something else about the instrument, and we can connect you with Johan. So another question is regarding the measurement techniques. So some of the flux measurements are collected in unit of mass per square meter in the plume, which is 2-dimensional. And then the wind speed as a 3-dimensional component needed to estimate mass emissions per unit time. Is this understanding correct?
Yeah. We measure, the unit we measured, there's a column is gram per square meter, and then you multiply with meters per second, and then you get grams per second out of that. Well, you have to integrate actually again. It's actually you get the grams per meter when you integrate along the you drive across the plume. So you measure gram per square meter, and then you drive across the plume, and then you get gram per meter instead in the plume, and then you multiply with meters per second, and you get gram per second. I don't know if that was clear, but
so another question, next question. Did you find out anything surprising or unexpected in comparison with studies done in other places?
Well, there's not so many San Joaquin valleys in other places, is there? No, it's kind of unique. I think that's several things. The CAFOs is of course something. There's been some studies in Denver, done in Colorado on the CAFOs, sort of similar, and we have sort of continued this work. So there will, in the future, there will probably hopefully be a paper on it. So there's a lot of different studies when it comes to CAFOs, where we compared it. We have the industries, which is, of course, I already showed that we were comparing it, and we were putting it to see if it was high or low compared to other industries, which and so on. So I think that it gives us a good understanding, and of course the industries in California, they had done a lot of work on abatement measures, definitely. So this is why they are low. I mean, I know also that the industries, for instance, in the South Coast, they are even lower. I think I would say that, you know, they are definitely as low or lower than the ones that we measure in the Bay Area. So a lot of work has been put in, and you can actually see that when you compare it globally, that it works. You know, if you do abatement measures, you get on the low range of these emissions. Of course, and then it's another question: why is there difference? Why is there the difference in the emission inventory reporting and there's still a kind of a gap between what we measure and what is reported, and that's sort of a learning to try to understand that. And I guess it's not so important for. It's important for the air quality modeling and things like this, that you have the right numbers coming out, that you understand, and how big one source is compared to other sources that you might have. I mean, how big is the transport sector compared to the stationary sources, compared to oil, gas, and so on.
Great, thank you. So the next question is the accuracy. This is a kind of long question, so I'll just, sorry. So is the accuracy of methane measurements high enough when taken over several iterations to establish a baseline for a facility's emissions for applying a methane reduction measure? I'll stop here. Oh, no, sorry, I should continue. So in other words, using the fence line measurements for pre and post treatment of the facility, for example, a control measure like technology or process change, would that give a regulator accurate enough data to update their inventory? Or are the error bars too wide, and other data like aerial LiDAR should also be used to tighten the error bars? So like my understanding, this basically asks, whether this data could be used to inform emission reduction measures, or they could evaluate some of the emission reduction technologies by pre and post measurements. Do you think the data is accurate enough to provide the regulatory agencies this information, or is the error bar too wide and we will need more measurements to complement the current measurement data we have?
I mean, it depends on what is your abatement. I mean, and again, it depends on, I did not, if it's, I assume it is a type of refineries and this is industries rather than CAFOs. I'm not sure if that was but we did it we have done sort of a stringent, more error analysis for the CAFOs, and we end up with something like 40% on the 95% confidence limit with the indirect method, something like this, because we are adding several errors together. Still, and then so that's like for the CAFOs, and then it's the question: is that good enough or not? That's really up to what is the question? You know, how much improvement are you looking for? Are you looking for a 5% improvement? Then the answer is no, it's not accurate enough. If you're looking for like a bigger improvement, that you want to reduce something by 90% or something, if you put in an abatement measure, then the answer is yes. So again, it depends. And yeah, I'm happy to discuss it if that's
So how about the refineries, Johan? Could you please provide some insights on refinery? Because I think we have done a lot of measurements, like you with the CARB contracts and also with your contract with South Coast AQMD. Is there any insight you could provide for refineries, like emission reduction technology in terms like for refineries? Based on
the thing is that very often, again, we have a direct method, which is we can measure 90% of the emission from a refinery. That's measured by sulfur, because that's in the alkane domain, and they very often correlate with methane and other stuff. So if if you reduce the alkanes, then you will get the methane. But of course, then there are others. Sometimes it's not true. Then you have to be very good in this methane, of course. So I mean, just by reducing, making sure that you don't have this alkane, any gas emissions, then you have really reduced. And then, yeah. And I should say that it's the indirect measurement. I mean, it's sometimes it's more difficult to work. Very often it's in places where we are measuring inside refineries, where we are working within the industry. Then we can sort of map. We can look at the correlations. We can see the sources, and we understand the patterns where there's methane and alkanes and so on. And then we get a much better. We can do this follow up in a better way. If you have to do everything from the fence line, if you have a big refinery and you have to do a fence line measurement and you want to follow up abatement measures, well, then it's a little more difficult, and you have to, and the uncertainties goes up. So again, it depends. It depends. But just to make sure that when we have. It's definitely so. If you reduce that, like you saw in my first slides in the Sweden in a port area where we've been measured for almost 20 years, we have measured a steady decline in the emissions of alkanes, and also it's the same for the methane, obviously. So I mean, it's sort of you can see that it's working. I don't know if that was an answer, but there was a comment.
Thank you. So the next question, was there monitoring in the community during the day as well as nighttime? Did you measure at all the communities where you measured the sources? Could you explain how you were able to measure during the nighttime in the community, but not so at the sources? Yes, that's a question. So like basically, whether we have done any community measurement both at daytime and nighttime, did we measure all the communities where we measure sources?
I mean, we have. We definitely. The project was. It was very important to do the community monitoring in the project, and we were focusing on some. We were not focusing on all of them, but we were trying to. We have quite a few communities on our list that we have been going through, but we have not we did not have a setup where we're doing a lot of averaging, because obviously if you're really interested in exposure and so on, you probably need to have a sensor there for 3 months or almost a year to see what's the real exposure for people, and we are making a snapshot thing and more a snapshot thing. But our approach was really like this, that we identify the hot spots and the emission things, and then we try to follow these things down in the communities. So we have been trying to work from the sources to the communities, rather than putting up things everywhere and doing it the other way around. And so we have focused on some of them. We have done more work on some of them, and and for some of them it's more relevant for some of them because they are closer to sources and so on. I mean, for instance, the Richmond where we were focusing on, it was we also had to do this AB 617 areas. We wanted to look at some of these areas. So that was also part of the thing. We did it also in the North LA. We were in some of these areas. We did monitoring, but there was not, and there was a landfill there, but it was not so much then. It was mostly methane coming out from it. So it means that it's not so relevant from the air quality perspective, of course, from the climate perspective. So, I mean, as you see, we've done a lot of work. We have many sources here. So we've done it's a big work, and we covered a lot of stuff. And of course, it would, in the best of all worlds, it would make sense that we came back and we'd make some more, in-depth studies on some things, maybe longer time or so.
Johan, if I can add, I think on your slide 6, this is also a technical answer to this, right? That for emission measurements, you're using the solar occultation flux method, which requires sunlight. Right, so it had to be done during daytime, whereas the other kind of tools we were measuring ground level concentrations and they could work anytime. So that's one of the reasons emissions were measured during daytime, but concentrations could be measured anytime, morning and night. Yes.
Yeah. Okay,
Yeah.
so the next question, did you find a time of a day, including when the condition average that the emissions were highest by source or by site? So basically the temporal variation of the emissions we measured in our study. Have we observed any specific time of the day with the highest emission?
We were able to detect some type of temporal variation in the ammonia emission from the CAFOs, because, and that's sort of what you would expect, that there should be so we could see some type of diurnal variation in them. So they were lower at like 4 in the end of the day, 4 to 5, or in morning than in the midday. We could see that. If we aggregate the data, if you put them together and average. When it comes to the industries, it's not so easy. I mean, industries, they have their own variability. They have other stuff going on. There can be like a leak, and there can be stuff happening and so on. So it's I mean, there is a diurnal variation in it, that the tanks, the sun intensity is highest in the middle of the day, and so some of the tanks which are they should get higher emissions. But there's so many, tanks are white, which is good. If they were black, it would be a real problem. But now they are white, and if you look at, it's a big chunk of oil in them, which cools down things. It makes things slow. So they're not so sensitive to ambient temperature. They are sensitive to the monthly temperature. They are slowly varying, definitely. And there's of course an impact of the solar radiation. And if you look at the API model, it's like it's predicted it's a 30% variation going from night to day. In that you can look at, and they have done studies by their own, and this is what we have been doing before. So we cannot really see a big diurnal variation from refineries, but they are very variable, and we are doing statistics. So in the end, it's basically the sum of all 3 days and 12 measurement statistics. That is our main thing.
Great. So the next question, what major differences did you find between communities when measuring the emissions? So Mark, if you don't mind, could you please clarify a little bit what kind of information you were trying to get from this question? It's kind of like short question. For ammonia emissions, what major differences did you find between communities when measuring ammonia emissions?
I'm not sure if okay. When measuring. Do you mean if we were,
so maybe from different perspectives, were you asking what's ammonia emissions, how do they vary from different the dairy farms they measured? If I understand correctly, is that a way to interpret your question? Okay, so basically what are the major differences we see for ammonia emission from different dairy farms?
Okay, the emissions. I mean, we see. There is a variability, as I showed, that we had it as an emission factor, because of course you need to normalize with the amount of cows that you have inside a farm. So and we did see that there was actually a variability from farm to farm, and it seems to and why there is a variability. I mean, of course, you can reduce the amount of ammonia emissions by how you work with the manure and things like that. I'm not sure if there were systematic differences in how these different farms were operated and so on, and maybe that's something to look into. I mean, we were not we were not allowed to be, I mean, we were not doing it, we were doing it in a fence line again. So we were not doing a specific study, and we didn't have full access to those different farms. And so we had to, you know, so I don't really have the answers. But if you look in the report, and there is actually there's a variability, or maybe a factor 2, between individual farms, and you can look at the statistics. It's sort of significant. So there are differences. It's not like a steady number. Absolutely.
So next question, based on the studies, is there a need to update the emission factors, for example, by EPA or CARB or other agencies, to get more robust emission inventories that align well with the measurements?
Again, is it a general is it for all of them, or for all different things now, or is it for the CAFOs, or is it I will answer generally. I mean, it's obviously there is something with the emission factors in the industries that we see a discrepancy between them, and we claim that it's not, that it's partly something that is in the emission inventory. So I think that should be aligned somehow. Definitely when it comes to the oil and gas sector, we have this huge difference in an order of magnitude when it comes to all the NMVOCs coming out from it. We saw a factor 2 for the methane. So maybe then we have to look into that's I don't know if the methane emissions are good. Well, I mean, we were quite. I mean, in that ballpark, when we compare to the scientific aviation, we had a similar. They measured similar numbers, sort of. So I'm not sure. So maybe it's not too bad for methane when it in our, at least for this study, but definitely for the NMVOCs, it's when it comes to ammonia, it seems to be. I mean, we have this difference, but when we have actually gone a little further, and also in the report, we actually make sort of a discussion where we know there's a diurnal variation which can explain. So I think that that diurnal variation puts the ammonia back to, it's not so different from some. So for some reason the emission factors ammonia might not be too bad, but it could be for the wrong. It should also be for the right reason, that you understand. Because then there's different type of cows and different type of management, and sometimes it's right for the wrong reason. So I think that we have shown that we have sort of a tool that could complement other tools, that we can actually measure directly on a farm, and we have another way of measuring the fluxes and so on. And I think emission factors, even if you get the numbers right once or twice or 3 times, you have to be sure it's for the right reason, and and that's not, and then you need tools, and you need to keep on working. So I don't think you should ever be satisfied with you should. It's an ongoing work, and I think that that's probably.
So
yeah.
So it basically provides some insight on the difference between the measured emissions and our inventory estimates. But again, we should caveat, we are still doing snapshot measurement, and we may need more information to really understand what is going on with actual emission from these facilities, right?
Yes, but I would like to back your thing. I mean, we don't really. I mean, snapshot is a very hard statement. A snapshot is passing once. If we do it, if you are for several weeks and you're doing multiple days, and in other studies we've done much more. We can do up to 20 days of study. Then it's more like. It's not a snapshot in the sense that it's like, the thing is, we have a systematic problem with the soft technique that it's only measuring in a day. So it's actually a day method. So you need to have some model to understand what is the diurnal variation. But for that reason, it's not a snapshot measurement, then it's a day measurement,
Mm-hmm.
So then you need to understand what could be the difference between day and night. But we can do a lot of averaging, and we can measure as much as needed to make sure that. So I don't think that we should call this a snapshot measurement, but it's not a measurement that where you can measure for a month, for 3 months, or you can average and you can aggregate. Definitely not. But yeah. So that's just a comment.
Okay.
But you always need to have, I think it's important that we make a measurement, and of course then you need to say that, okay, what does this measurement represent? It measures in the day, and anybody can take our data and they can do their own modeling, and they can figure out, okay, how much variation should there be, and what do our measurements tell you? So it's not like our measurements had to tell what's the absolute annual emission or something. It's something that it's a tool, part in the tool. It's a good tool, it's something you have in your toolbox, and it should fit together with other stuff, obviously, models and other measurements.
Great. Very good point. So I guess it's a follow-up regarding the question we just talked about, the ammonia emission from dairy farm. I think he was trying to understand why they are different from models. Could you explain a little bit? I think you mentioned that some of that in your previous answer. So why are our measurement of ammonia emission from dairy farms different from the models, from the model estimations?
I mean, I think that the main thing is this: that there's a diurnal variation that shows that in the day when it's hotter, and if you have sunlight, then it's a much stronger than the emissions. The ammonia emissions they are higher because they are not. This is not the case for. There is also diurnal variation for methane, but methane is produced in the soil by the bacteria, and they are not so exposed to, they are not they have their own life, and then the methane seeps out. But the ammonia has there's some type of diffusion layer on the ground that depends on how much ammonia emissions you will get out, because it's liquid phase, it's like urea in the ground, and then it's like there's some type of thermostat equilibrium with the gas, and then and I think that the temperature is and the sun is actually destroying that layer, and it's making it much easier for the ammonia to leak out. So you can see differences, and we have done some following work already a little, but as part of the report we did already this discussion, and we said up to 70% of the 100% could be that, looking at some papers. And now we have even looked at a model by the EPA. We got the model from the EPA where they do the annual variation. So and that sort of showed the same thing. So at least we can take away maybe 70% of the 100%, and then we end up with the uncertainty. So I think we are not too far away with ammonia as an average. Then there are individual farms where there's differences much bigger.
Great. So I don't see any more questions in the chat right now. Appreciate everyone coming to the seminar, and appreciate you can present your presentation and answers to all the questions. I'll just wait for a couple of minutes to see whether any more questions coming up, and we are almost reaching our 2-hour limit for this seminar, but I'll stay here for a little bit while and see whether any more questions coming up. But thank you, everyone. Thank you, our PIs, for the presentation and answers for all the questions. It was very good discussions here.
Thank you for listening and discussing. The question asking when the presentation and slides be posted. After this presentation, I will work with our research admin staff. We will make sure the slides can be posted as soon as possible, and we'll send a link to everyone for the presentation. Any more questions or comments for the projects and the presentation? If not, I think maybe we can end 5 minutes earlier than we scheduled. Thank you again so much for everyone to come to this seminar, and thank you, Johan, for your hard work for the projects and with the team, and also this great presentation and all the discussions we have during this seminar.
I'm looking forward to work with you again in the future.
Yeah, thank you.
So again, like I mentioned, there was my email. I can put in the chat again. So anyone, if you need more information, please feel free to contact me, or I will have my supervisor's email, Ablash. So please feel free to send us an email if you need further information, or if you want us to connect you with a PI for future discussions. Thank you so much. Really great discussion. Really appreciate everyone coming. Thank you, Yuhan, again. Thank you.
Thank you. Thank you. I will send you an update. I had some small changes in the presentation, Yang, you from there.
Great. Yeah, if you could share with me the slides right after this this seminar, and I'll work with admin staff to make sure we can post the slide as soon as possible.
Yeah, but I do that as a PDF or.
PDF is fine.
Yeah.
Great. Thank you so much, everyone. I'll
you.
close the meeting for now. Appreciate everyone to come to the seminar. Bye.
Bye-bye.